Hello everyone. Now we are going to start modeling an important system which is a fan driven by a motor. So here let's say we have a fan which is controlled by a simple motor which is a DC motor. So this is going to be a good example of an electromechanical system where electrical control of DC motor will result in variation in speed of fan which is connected on the shaft of the DC motor. So we need to understand first what is exactly the behavior of a fan load from the DC motor perspective. So usually the fan load or torque exerted by the fan load, let's call it as TL, the load torque, which is proportional to the square of the speed, which is omega m. So the load torque is proportional to the square of the speed. So usually this is the case, and let's say the constant of proportionality is C, then it is going to be C times omega m square, and this is expression of TL. Now based on the value of C, you can actually model a fan load and you can apply various voltage and current at the motor side and change the speed of the fan. So here we are interested in simulating such a system where we are varying the voltage and current, and this voltage and current, which are electrical quantity, will affect the load torque and the load speed. So let's assume here we have a motor and its shaft is connected to a fan. So a fan is nothing but a simple construction. Let's say it's an exhaust fan or simple a ceiling fan having, let's say, 3 number of wings. So this is a fan load which we are required to actually simulate, and this fan load, according to its aerodynamic characteristics, is going to have different speed and different torque values. And also we need to consider whatever is the inertia of the fan load. So basically this torque speed characteristic can be modeled in a MATLAB environment like this. Equation is the first one, and we can have inertia also added, which is going to be the weight of all the wings of the fan and maybe the rotor inertia of the motor as well. So here let's say this is a DC motor and we require a DC supply which is going to power it up the motor. So motor is driven by this supply, and voltage and current are going to be taken from this supply voltage. Application, where you will find this kind of an application in reality, and how you can actually simulate a more realistic situation. So this is just an image of a fan, which can be an exhaust fan or any other type of a fan, where you have some 2 terminals coming out of this, and here inside of this is going to be a motor. So on the central part here, this is going to be a motor, and which is given the supply from either AC or DC. That depends on the type of the motor. So let's go to the Simulink environment now and simulate this situation of DC motor driving a fan load. So here I have taken a subsystem which represents a fan load, basically an aerodynamic drag. Let me show you what is inside this subsystem. So here these are the 2 connectors R and C, and basically they are physical modeling connection port of the subsystem. So R stands for the rotating part and C is a casing part which is going to remain fixed. So here we have implemented the square law, which is the speed omega and the torque are correlated by these equations. What you see inside another subsystem is just the multiplication of omega with itself, and therefore you have the omega square and a gain which is a constant of proportionality and which is this value minus 8 e raised to minus 8. So here, if I go one level up, then we have this system where this is nothing but an aerodynamic drag block, which is the name given to this block. But actually we have used this block earlier and it's a torque source. So this ideal torque source is going to apply torque on the shaft of the DC motor according to the speed of the load. Now how do we get the speed? So for getting the speed, we have a motion sensor, or this block is ideal rotational motion sensor. So the value of the omega is given to this block and the value of the torque is given to this block, and therefore completing a loop. Let's come out of this system and we are going to connect R with the rotating part and C with the casing of mechanical system. So let me keep this block over here and now take a DC motor from the electrical Simscape toolbox. So here we have a DC motor. From its block diagram you can see these are the two brushes and the armature of a DC motor, and the positive and the negative terminal for DC supply, and C and R are nothing but the mechanical terminals, or we can say mechanical ports. So let us connect R with this R and C with this one. So here I have connected R and C. Let us take a DC supply which is going to give some DC voltage to this motor. So I have searched DC supply over here. I am not getting any result. Probably I need to search out with a better technical keyword, and which is nothing but DC voltage source. So here we have a DC voltage source, and let me connect with negative, and in positive I want to read out what is the value of the current taken by the DC motor. So for current I need to have a current sensor or an ammeter, which is, let's search out for the current sensor. So here we have a current sensor, and we need to make sure that all blocks which are of equal color, they are connected together. So here this current sensor is also in the blue. Probably if you have any other ammeter or a current sensor which is going to be different one, then you will not be able to connect to this blocks. So here I am making a search again, and there may be a current sensor of 3-phase type, which is not the case right now, or let's say a current measurement system. Then we will not be able to connect this one, right? Let's try see whether we are able to connect it or not. So for time being I'm disconnecting this, and let's understand what is the difference between a current measurement and a current sensor. So if we connect this one with this, we are not able to actually get it, because this block is basically from another library, and it is from a fundamental Simulink library. So here, and this one is a Simscape library block. A Simscape library block will be able to connect with the Simscape one, not the Simulink one. If you need to connect, you will require Simulink to physical signal converters. So I'm going to clean up my diagram and let me make it a little compact. And here we have a electrical system ready and a mechanical system also ready. Now out of this, what we need to measure is, let's say, keep track of voltage. We are going to fix up the current and speed and torque. So let's connect the current over here. If you see, I'm not able to connect properly to this scope because it's a physical signal. It's not a Simulink signal. So what we need is basically a physical signal to Simulink converter, and then give an input to this and take an output like this. So here we have a physical signal to Simulink converter. So here we'll be able to read out the current. Now let us plot some other values which are speed and torque, which are mechanical. So I'm interested to plot speed and torque of this subsystem. So I'm going to go inside the subsystem. I want to get signal which is speed over here and torque over here. Now, how do I connect all the signals outside of the subsystem? So there is an easy way of doing this where you cannot route your wires, or where you cannot route your connections, whether they are electrical, mechanical, or any thermal or whatever, but they are in different subsystems. So here, if we want to get out these signals, we have to send those signals to another point, right? So once you have a complicated system, or once you have many such signals inside each subsystem, you are going to have trouble of taking those signals out. So they are not just like a port, but instead of a port, and instead of keeping it as a connectors, we can keep it as goto and from as well. So here I want to send the signal to outside. I'm going to write a goto is nothing but a Simulink routing, where we need to give it a proper name, and that signal is going to be available to whatever point we want to send it. So we are going to send the speed command, and let me connect the speed to this. And because we do not have the physical signal connection, we need to require a physical signal to Simulink converter. So here I have PS to Simulink converter for one goto block, and I'm going to copy with a right click for torque block, and I can copy this another goto as well. So here we have, when you click on the goto, you need to give a tag which is going to be referred elsewhere. So this tag is nothing but a name given to a signal, and you can refer it elsewhere, anywhere in your diagram. So here I have a goto tag A. I'm going to connect torque over here, so I'm going to write torque. Okay, so here is a torque, and this one is the speed. So I have assigned the name of these two different tags, and now I can probably connect like this and like this through this physical signal to Simulink converters. So now I have sent these two signals, and let me get these two signals out near to this scope. So in order to receive those signals, we can write from. So from is another signal routing component which will help us to plot all the quantities at the same time. I'm going to take one from and another from, and I will be connecting to the scope. So here in the from also I need to assign the goto tag. So my tag name is, let's say, first is speed. I need to remember the upper casing and the lower casing because I have typed the capital S for speed tag name. So I need to assign that like this. So I have a speed tag and a torque tag. So all the speed and torque will be coming over here. Now what you see highlighted in this from block is no matching goto block. So what you see here is the goto and the from are not matching, right? So probably let's go inside the subsystem and try to figure out what is the issue. Here we have a speed and the torque, and the names are exactly same. So here I have a goto tag. Okay, the mistake which I am making over here is the tag visibility. So the tag visibility is a local as of now, which means in a typical subsystem or within a subsystem it is going to be visible. So if I change it to be global, then the speed will be taken care. I need to also change this torque to be global as well. So now here we have the torque and the speed all together, which are actually going to be now reflected in the main diagram, right? So probably as you have a mechanical subsystem, if I have another complex system where it's a maybe a DC drive or a DC controlled supply driving a DC motor, then you have an electrical subsystem as well. So when you have many such subsystems and you want to plot some results, or when you want to refer some signal from one subsystem to another subsystem, you can make those signals as global. So here the from and the goto are the very important parameters or very important components for signal routing. So now let me configure the DC voltage source. The default value is 0. Let me keep it at 100 volt. Let's open up the DC motor parameters. So what you see here is the model parameter by equivalent circuit, and the armature resistance and inductance. I think you can refer it more detail with the help, but the fundamental important part is a back EMF constant, which is this value, and which is its unit is volt per RPM. So per revolution it requires around this much of volt, and that is a default setting. So let me keep the default setting over here, and as I said, we can actually connect some inertia over here. So let me find out the inertia block and connect it to this point. So let me rearrange the blocks again. So here I can just clean up my diagram, and I can connect the inertia by rotating it with Control R, and probably I want to connect like this. So here we have an inertia, and let me keep as a same value, 0.01 kilogram into meter square. So this is going to be a inertia along with the aerodynamic drag, and which is connected to the DC motor. Now speed and torque are available. Let's run this simulation for 20 seconds, and let me save in to my folder where it's a new folder, and my file name is DC_fan, so that I will remember what is this model file. Probably if I hit the run button and almost everything is ready, we are now waiting to see the current, speed and the torque. So let's see, let's compile the block diagram, and probably you see many errors over here. So what are the fundamental issues, or how do we actually read out this diagnostic viewer? So here is an important line: each physical network must be connected to exactly one solver configuration block, and we do not have any solver configuration block. So probably we require a solver configuration, and so let me connect the solver configuration over here. I also have not connected any references. So whatever is the current, voltage and speed and torque, they will be with reference to some point. So we need to figure out those points. So I need an electrical reference, or it is technically called a ground connection. So here I have a ground connection. Probably this one is a black. I will not be able to connect with my Simscape block. I need to find another ground. So let me find out another ground, and here probably you can check out which library this block belongs to. So this is going to belong to spatialized power system, fundamental blocks and elements. So let's select this ground. So this ground is also black, and we need to figure out something else. Let's say electrical reference. Okay, now here is an electrical reference which is blue color, which is matching with the Simscape. Okay, fine. Look at these two blocks. They are exactly similar in symbol. They are also similar, but we need to figure out what kind of simulation we are doing. And if we are using all Simulink blocks, which are basic Simulink black color block, we can connect this ground as well. But right now we are using the Simscape, and therefore this ground will not be able to connect. Another reference point for this casing is to be a rotational reference frame. So I'm going to connect this with a rotational reference frame. So here is the rotational reference, and this reference I need to connect to the casing part. Okay, my diagram is now looking okay to hit the run button. But let me do one thing. It may not be quite aesthetic, or it may not be like quite good in terms of where you connect this wires, this connectors, and this maybe scope and everything. So what you can do is you can go to format and use the auto arrange block. You can go to format and use the auto arrange block, which is going to make the layout simple. So if I click on auto arrange, probably my blocks are arranged properly. So if you have a lot of mesh with your connections, let's say this one is going up like this one is also you have connected like this, and it's probably not perfect, right? Then the auto arrange is going to short it out. Okay, so with this arrangement, we are now ready to hit the run button and see the output. So here we have the output, and you can see these 3 signals which are coming like this. Now, do we have any idea about what color represents which signal? So what's the solution? Yes, you go to view and show the legend. So you have to click on the legend over here, and you will be able to see all these signals. Now whatever has come over here is all PS to Simulink converter. So let's go back to our diagram and actually name them, and so that we are able to signal them properly in the scope as well. So in order to name a typical signal, you just have to double click and type the name. So here I'm writing current. So you double click on the line and type the name you want to give. So here let me make this scope a bit bigger so that we can see the names of the signal. So here I'm going to give a speed signal, and I double click over here and I have a torque signal. So now let's run the simulation and let's see the output. So here, yeah, your speed is increasing. The torque is like this, and you can zoom in with the torque, and let's see what is the exit torque value. It's a little negative value coming up over here, and if I zoom back again, the current is almost constant at around 25 and 26 between these two values. So this is what is happening with the speed. Now what we are doing here in this diagram is actually we are applying a fixed voltage, which is going to result into the fixed value of the current, and because we have an inertia load, we are going to observe the change with the inertia as well, right? So this is 0.01 inertia we have connected over here. If I disconnect this inertia, do I going to have any different observation? So okay, let's keep this in mind. We have this variation of speed and torque and current, where the speed is continuously increasing, and let's try to understand what happens without an inertia. So here I have deleted the inertia block, and I'm going to run the system again, and let's see what is happening. So what has happened to the speed is now almost constant. So because of the inertia, the speed was gradually increasing. But now we have this RPM, let's say speed unit, in terms of around 469 units. So this is the effect of an inertia. If you change an equation over here in this subsystem, or maybe the gain over here, and maybe if you want to implement some equation like 3 plus omega m square or 3 plus 2.3 omega m square, you will be able to do it. So let me go back to the main diagram, and instead of a fixed voltage source, let's disconnect this and let's connect a control voltage source. Now, why do I need to connect a control voltage source? I just want to imitate, or I just want to realize a situation where we are gradually increasing the voltage, right? So what will happen to a DC motor if you gradually increasing the voltage? Its speed will also gradually increase. And here we have taken the torque, which is proportional to square of the speed. So let's see what happens when we change the voltage gradually, not fixed 100 voltage, but let's say we want to increase the voltage in the step of 5, right? So let's say every second the 5 voltage is going to increase. So that is a linear voltage rise, and let's understand what will happen in this case. So here I have a controlled voltage source, and probably this one is a black. I'm not going to try connecting this one. So let me find out another controlled voltage source, and let me check out this time about the foundation library. Probably this one is going to be the best suitable, and I can connect like this. Okay, so my negative wire is connected, and I can actually route another signal as well. So what is a control voltage source? Basically it takes an input from here, and whatever is this input, that will be the output voltage. Here the fundamental output voltage V equals to Vs, where Vs is the numerical value which is given to the physical input port. So now I can take up a ramp block. What is a ramp block? Ramp is nothing but going to continuously increase the value according to the slope. So here what I want is, in the 20-second time, I want to rise the voltage from 0 to 100. Instead of fixed 100 value, we want it to rise from 0 to 100. And what is going to be the slope in that case? It's 100 by 20, right? So we want to get 100 voltage at the end of 20 seconds, and therefore the slope is 100 by 20, which is 5. So I keep this 5, and let me connect over here. Okay, again a mismatch because it's a Simulink block and this is a Simscape block. So what we need is Simulink to physical signal converter. So here I have a Simulink to physical signal converter, and let me connect these blocks now. And probably what we have done is changed a DC supply voltage, which is going to rise from 0 to 100. Now what will happen to the fan load? So fan load speed is going to change, and it is not going to be the steady speed from the beginning, and at the end of the 20-second we'll get probably the highest value of the current and the speed. And let's observe what is the torque coming up. So let me simulate this again, and let's see the results. So here is the result, and probably what is the nature represented by this blue line? So the blue line is basically the speed, and the orange is the torque, and what we are getting is some relation which is exponential, right? So because we are increasing the voltage like from 0 to 100, and the current is also increasing like this. So let me zoom in with the current, and the current value is around 25 ampere. So which was the earlier case where we supplied 100 voltage directly. So in this simulation we are able to understand what will happen if you change electrical parameter to mechanical parameter. So whatever are the effect on the mechanical things, that is what we are observing. And probably the exponential nature is coming up due to the equation we have implemented as speed and torque. So look at your torque value, which is going almost constant. Your speed is rising exponentially. And now if you plot or if you see the relationship between the speed and torque, one value being fixed almost and the other increasing, this is going to be a square relationship. So this is about the DC motor based fan. And what is a effective learning outcome is how you can use the Simulink signals to apply a controlled voltage source, how electromechanical system works, and how from and goto are utilized here for subsystem signal routing. Thank you.